So in this section of linear independence and Roskian, there's two things I want you to take away from this section. Just the basic notion of like what we're trying to do big picture in solving initial value problems and just kind of this idea of what does it mean to be independent and how to find the Wronskian. If you can do those two things, you're good. There's just a lot of details in this section that kind of go over your head because it's the first time you ever hear about it, and you kind of need a lot of other stuff to really truly understand it. Like if you haven't taken linear algebra, a lot of this might sound weird, especially when we take the determinant. So don't think that this is a section that's gonna like inhibit you in doing well. At the most, this ends up being, one or two questions on the exams. Usually it's just like, hey, can you do a Wronskian, right? Can you show something as independent or dependent? Like those are the two main questions they ask you. Or like, what's the interval of the unique and existing solution? Which on a computational level, they're not bad. They're quite straightforward to do. But understanding all of this is very complicated. So we'll try to piece it together, little by little, but don't let it overwhelm you or feel like, oh, because I don't get this section, I can't do the rest. Trust me, this is not the case. We could actually skip this section and just go into the rest of it, and you'll have no issues, right? This is just kind of like the mean value theorem, essentially, of chapter three. It's useful and its justification for what we do, but it's not necessary to use in our computations, right? So just kind of think about it that way. So um, we want to generalize several of our discoveries in 3.1 to any differential equation, mainly second order. Um, and so to begin that idea, let's just kind of set up a differential equation. So we state the structure of any initial value problem, right? So to remind you of what that is, the differential equation will look something like this. An of x, y to the nth derivative, plus an minus 1 of x, y to the n minus 1 derivative, and so on and so on. Again, it's a confusing notation just because there's so many things going on, but at the end of the day, it's not something that you have to think too much about. What this really says a lot of the times is that the coefficient of your dependent variable y can be anything but y. Okay. But we're mainly looking at when that an of x, like that x function, is just a number, right? We bring it down to a number, and then we're only going to the second derivative, so who cares about the rest of it, right? And then right now we're just saying g of x is equal to zero. But this is getting rid of all of those like super assumptions, right? We're kind of removing all of that and going to the base of it. And so the initial conditions that you will get is you pick any x value, so x naught, and from there you kind of use it for all of them. And you basically just go up in derivative, right? And you stop one derivative less, right? So if you have an nth derivative, the highest the initial condition will go is to the n minus 1 derivative. And the reason for that is if you have a second derivative, there are three terms, right? Which means we only go up to the first derivative because we need one for y and we need one for y prime. We don't need to do one for y double prime because in our process of solving the differential equation, we don't actually need it. We don't use it, which is good. One less thing. And we get y of n like that. Minus 1, sorry. So that is the structure of any initial value problem for a differential equation that we're working. Now, the key thing is this is a linear. It's still linear. We're not doing nonlinear here. So it's linear. Nonlinear, this goes out the window and we have other stuff. Okay, so there's this theorem. Again, don't need to memorize it, just understand the basic principle of it. And it states this, right? The existence and uniqueness theorem of linear differential equations. And all it says is this. Let those coefficients so an minus 1, and a naught of x, and g of x be continuous on an interval I. Now, if you forget what is continuous, it just means no division by zero, no jumps, no vertical asymptotes, all that stuff. You can draw it with your pen or pencil on an interval I. So usually the interval we like is negative infinity to infinity, works for everything, but that's not always the case. And so this is solely for the fact to negate a weird scenario where if the first coefficient is zero, then you go down 1 degree and then it just creates a little bit of headaches proving it. So the an of x not equaling zero, it's just a formality to make our life easier. It basically removes weirdness from our proof. So don't think too much about it. It's just a thing we do. Basically, if you're proving something for quadratics and your first term, the coefficient in front of x squared could be zero, it's no longer quadratic. So the theorem for quadratics now works for linear. It just kind of creates this headache. So again, it's kind of one of those things. If x is equal to your initial condition value, x naught, so if x equals x naught is any point in the interval I, then a solution y of x exists and is unique. What does that mean? All it means is if you have a differential equation that looks like this, then if you find an interval where it works, you get a solution. Like it's guaranteed. Now, why is this important? Well, there are functions that don't have that property, namely Navier-Stokes, which is a huge one in fluid mechanics. The existence and uniqueness of Navier-Stokes is one of the seven millennium problems, right? So, but for second order, linear differential equations is a lot easier to, solve versus like a PDE, partial differential equation. That's all we're saying is that you get a solution as long as it follows these characteristics. And again, you might think that doesn't really translate because I'm not seeing any numbers or any functions. So let's do an example for that so you can kind of see. So they might ask something like this. Find the largest interval in which the solution of the IVP is certain to exist. So here's the differential equation. X squared minus 3x y double prime plus x, oops, that doesn't look good, y prime plus x plus 3 equals 0. And then we're told y of 0 is equal to 2 and y prime of 0 is equal to 1. So before we actually continue on, we're going to go back to this existence and uniqueness theorem. So this is a very generalized version of it, and the proof of it's very complicated. So, but I'm going to simplify this for second order because we'll want to be able to do this for second order. Um, for second order differential equations, we want to express our differential equation in the form y double prime plus. So essentially what I'm doing is I'm dividing out a1 in this case. So here, I'll do it this way. One defined expression in the form. So a1 plus a2 of x y prime. Oops, I'm going backwards. It's the other way around. A2 of x, a1 of x, and then a naught of x equals g of x. We want to isolate. This just makes the process, because otherwise the process becomes way more challenging. And if you're wondering, like, why are we doing this? It goes back to what we did much earlier in chapter 1, where we had to isolate y prime dy dx. It's the same principle. So that's all we're doing, is we're rewriting it like that. So some people will write it like this, like p of x y prime plus q of x equals, like r of x, right? So we're making it in a form where it's just easier to solve for these intervals. Otherwise, you kind of have to do a little bit more work, and we don't want to do that. And you're not going to really do it beyond second order in this class, right? So now we can do this problem, knowing that we're going to manipulate it first so that we can get it in this form that's very useful for us. So step 1 is going to be isolate, uh, or not even, yeah, isolate y double prime. So we're going to isolate y double prime. And so what we end up getting is y double prime plus x over x squared minus 3x y prime plus x plus 3 over x squared minus 3x equal to 0. And then step 2 is going to be find the points of discontinuity. Okay, so really just find domain slash points of discontinuity. So what causes division by 0 is what you're really asking. And so you look at the first one, so x over x squared minus 3x. That translates to we don't want the bottom to be equal to 0. We only look at the denominator. That's what matters. And we end up getting that x times x minus 3 equals 0. And so x equals 0 or x equals 3. And we look at the second one and we realize that it's the same thing, right? X plus 3 over x squared minus 3x. And we still get x squared minus 3x equals 0. So x equals 0 or x equals 3. So those are our points of discontinuity, and therefore our interval is going to be negative infinity to 0, union 0 to 3, union 3 to infinity. So that is the intervals of our solution, right? Interval of solution. And we analyze this and we say, okay, we look at our x values right here. Step 3 is find domain, sorry, better word, interval that contains initial condition. So y of 0 equals 2, y prime of 0 equals 1. Again, that's x and that's x. X equals 0, right? And you think, wait a minute, I made a mistake. Or did I? Right? Because does it contain 0? But I made a mistake. So this should be 1, not 0. I just wrote down the wrong number. So in that case, you would say no solution. Like those boundaries are no good, right? So I just wrote down the wrong number. I was looking at the wrong problem. But now let's correctly put the number down. So that's 1. So x is 1, and that's going to be between 0 and 3, right? So x is between 0 and 3, and that's my interval. And we're done. That's how you find the largest interval for the solution. So now we kind of investigated the idea of a solution existing in an interval. Now, you can have more than one solution exist in an interval, and we'll talk about that in a second. But the big thing that we're going to talk about in this section, beyond just, okay, we talk about what the differential equation is, right? It can be this generalized IVP, initial value problem, or boundary value problem. We're just going to focus on the initial value, really. And it can be any function as a coefficient. It can be equal to any function. And we show that any solution exists in the worst case, right? As long as we just have a domain that works. So in order to solve these problems long term, we're going to have to be able to essentially break it up into two components. And that is where this notion of the homogeneous versus non-homogeneous differential equation comes into play. So now we're going to be a little bit more specific on what that means. But we've mentioned it before, and all it means is equal 0 or not equal 0 if you want to think about it. So really it's just a definition. You see the word homogeneous, equals 0. If you see the word non-homogeneous, not equal to 0. That's all it is. So a homogeneous differential equation is when it equals 0. That is an of x, y to the n, plus dot dot dot, plus a 0 of x equals 0. Okay? That's all it means. Just equals 0. A non-homogeneous differential equation is when it does not equal 0. That is our differential equation is just equal to g of x, given that g of x does not equal 0. I'm going to write this over here somewhere. Just in case people are confused by this, the nth derivative of y. If it has parentheses around it, that just means derivative. Otherwise, it would look like an exponent. So we are going to focus on non-homogeneous 3.1 to 3.4. And then 3.7 is, sorry, homogeneous is 3.1 to 3.4. Non-homogeneous is 3.5. And then 3.7 is back to the homogeneous case. And then 3.8 is the non-homogeneous case of 3.7. Right? So we go between the two. Now, with that, we are going to generalize the notion of any solution and what that solution is, what it means to us, and how it works for any differential equation. So the, sorry, general solution and principle of superposition. The solution to a nth order differential equation of the form an of x, y of n plus dot 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 plus a naught of x equal to g of x is usually described as y of x. Right? That's really what it is. It's just y of x. Most textbooks actually use a different letter. They use like phi. So sometimes they'll use phi of x, right? Like that's the solution to this equation. Now, what this solution can contain can be many parts to it, okay? So y of x can, I'm going to use phi just so I can use different, actually no, that's fine. Y of x can contain many terms. So we say that if part of y of x is y1 or y2 or y3 or so on, we saw that the sum of two solutions was a solution. So why not say that y of x is equal to y1 plus y2 plus dot 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 plus yn is also a solution? It turns out it is. And we call that the principle of superposition. It turns out it is. So that's where we're going to introduce the principle of superposition. Now, if you are in circuits engineering, sorry, electrical, I should say, or mechanical civil, where you're doing like truss analysis or you're analyzing nodes, I will tell you right now, and for sure in electrical engineering, because I think Kirchhoff's law, if I remember correctly, is the whole principle of is all based on principle of superposition, where you can analyze different parts of it individually and then combine the solution at the very end, right? Like that's a very important concept in engineering. So what it states is the following. Okay. And it's going to be kind of, confusing the first time you read it. So let y1, y2, dot, 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 yk, and I'll use n because n is fine, be solutions to the homogeneous, we're going to do homogeneous only right now, homogeneous nth order differential equation on an interval I, then the sum of the solutions is also a solution. That is, y is equal to y1 plus y2 plus dot 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 plus yn. Okay? Now, we showed any multiple of a solution is also a solution. So y equal to c1 y1 plus c2 y2 plus dot 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 plus cn yn. And that's the principle of superposition right there. It always ends up looking like that. It's just we're going to call this a linear combination. Um, this summation called a linear combination. And so all of your answers are of this form. And if you think back to 3.1, it was just C1 e to the RT plus C2 e to the RT, right? So this is just saying it works for any size. And that's the principle of superposition. And just to make that obvious. So in this, we note two things. Okay. Um, the solution of the form y equal to C1 y1 plus C2 y2 plus dot 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 plus Cn yn is called the general solution. Solving for C1, C2 dot 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 Cn makes the particular solution. So there's a different notion right there. And beyond that, we can actually talk about the general solution in terms of something more specific, which we're going to call the fundamental set of solutions, but we'll get there in a second once we talk about the Wronskian. So now that we have this way of putting solutions together, there's a certain property that we want to ensure they have, because if it doesn't, it just makes it harder to work with. And that's the notion of being independent, right? And so that's going to be the next thing we talk about is linear independence and the Wronskian. Well, actually, let's just talk about independence and dependence. So, believe it or not, you have actually been working with the notion of independence and dependence ever since you started algebra. And you just never called it that because it didn't make sense to. But if you have ever had to combine like terms, that was linear independence and dependence. Okay? And that's how I want you to think about it. Things that are linearly independent essentially means you cannot combine like terms. Things that are dependent means you can combine them because they are like terms, right? And if you think about it that way, that's all it is. Okay. So, a set of functions in linear algebra, we say a set of vectors is a linear combination if it is written as C1 f of x, f1 of x, plus C2 f2 of x. Actually, I'm not even going to write the x. I'm just going to write C1 f1 like that. C2 f2 plus dot 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 plus Cn fn. That's it. A linear combination is superposition. You're just combining a function with a constant, right? It's the same thing. They go hand in hand, which is great. A set of functions is linearly independent. Some people define dependent first and then independent. Some do it the other way. I like to do independent first. If the linear combination is homogeneous and So linear combination, I'm not gonna say homogeneous, is C1 F1 plus, it is homogeneous, but I'm not gonna say it that way. Just gonna say equal to 0, which again, that just means homogeneous. And the only way that you can find a solution, or the only way that you can combine these functions together, is if all of the constants are 0. If any C value is non-zero, and makes the equation 0, it is linearly dependent. Okay. That's the difference between independent and dependent. Again, this is a very complicated idea the first time you see it in this notion. But if you think about it in the context of, combining like terms, all I'm saying is that if you can combine like terms and get 0, it's dependent. If you cannot combine like terms, and the only way that you could get rid of everything is by putting a 0 in front of it, it's independent, right? So let's just practice an example. Is x squared plus x plus 1 linearly independent or dependent? So part of this too is being able to deconstruct a function into like components, right? So first thing is we're going to identify your F1, F2, F3, right? So it doesn't matter which one you call which, it's a personal preference, right? So there we go. I've labeled them F1, F2, F3. Step two, actually, you know what? That should be step two. Let's make that step two. Step one is formula. I always go back to the notion of what's a formula? So I see the word independent. That means C1 F1 plus C2 F2 plus dot 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 plus Cn Fn equals 0. You can put as many as you want or just write the generalized formula. Okay? So that's my formula. So I identified F1, F2, and F3. Now step three is going to be check for non-zero terms. Here's the thing. This is one of those things where you need experience to do this, and that's where the Wronskian comes into play because the Wronskian is not experience, it's just a formula. But for something like this, you kind of just have to know how functions behave. And so this is one where you technically should know from like algebra that you can only combine like terms if they have the same degree and the same letter. Okay? So if I said, actually, let's make that step four. Sorry, I'm kind of thinking about this in a better way. Step three, plug in. So C1 x squared plus C2 x plus C3 equals 0, right? Now we're going to check for non-zero terms, right? Can I think of values that are not 0 that'll cancel everything out, right? And just to be clear, you're only doing it for C. X doesn't matter. We don't care what X is because that's not the point. It's the coefficients. So you say, okay, C1 x squared plus C2 x plus C3 equals 0. Well, if I make C1 equal to -1, C2 equal to 1, and C3 equal to 0, only one of them has to be not 0. So, right? Then I get negative x squared minus, sorry, plus x equals 0. Can x squared and x cancel each other out? Okay. These cannot cancel. Now, I know what some people might be thinking. Well, what if I just set x equal to 0? But again, I don't care what x is. Um, this is independent of x. We have to make sure that we're doing it from a coefficient perspective um, by c values. So C1 has to be equal to C2, which has to be equal to C3 equals 0 is the only way. Because 0x squared plus 0x plus 0 is equal to 0. So we say it's linearly independent. Proving something is linearly independent is more challenging because you're basically proving that nothing works besides 0. And that's a difficult thing to do. And that's what the Wronskian helps you do. Now, proving something is linearly dependent is much easier because you just have to give me one case, right? Just one example of it not working. And you're good. You're done. So let's do that next. Is x squared minus 3x squared plus 2. Do I want to do it with the 2? Now let's just do it like this, just to make it more obvious. Is this linearly independent? Wouldn't matter, but I don't want the 1 because it's just not necessary. So, formula. Again, you just count how many terms you have, and that's all you have to write down. CF1 plus C2F2 equals 0. You only need 2. That's how you can kind of memorize it. Step 2, find F1 and F2. Do I need the 3? Doesn't matter. But let's just all include it. There we go. Step 3, plug in. Now, here is where you got to think about, okay? Find non-zero C if possible. So you say, okay, can I combine like terms? That's really what you're asking yourself. Can I combine like terms to get rid of them? And I think to myself, you know what? C1 is equal to 1 and nope, wrong one. C1 is equal to 3 and then C2 is equal to 1. So then I plug it in. So this is linearly dependent because I found a combination that's not 0 that works. Now, if you're wondering, but 0, 0, what if that works? Well, guess what? It works for all of them. So the question is not whether 0, 0 works or just all zeros, because 0 always works for all of them. Okay, we can write that down. 0 works for every case. Again, it's called the trivial solution. What I am asking is, can you find we call it a non-trivial solution? Call this a non-trivial solution. That's all we're asking. Now, if you're wondering, why does this even matter? Well, it matters because if you run into a differential equation with a dependent answer, or you get a dependent solution, you're not going to be able to solve for everything. You're going to not have enough information. That's the problem you run into is there's a lack of information with dependent solutions, and that's why we try to avoid them, right? So that is the whole reason we do it. It's just to avoid lack of information. So where does this Wronskian thing come into play? We've mentioned it several times. Well, the Wronskian is just the independence test. That's it. It just allows you to show something is independent. And so now we'll define it. So this is one of those things where I tell students, um, the Wronskian, it's just a thing that'll be on the exam. It kind of has to be because otherwise we wouldn't teach it to you. And it's just, can you use it or can you not? It's like Euler method. You either know how to do it or you don't. So you don't have to understand the why so much. It's more of like, can you use it and answer the homework questions? And the exam should be similar enough to that. So you don't have to dive too deep into it. So this is a definition, so we define what it is, and then from there we make it into the result we get from it is a theorem. Okay. Suppose, and I'm only going to do this for 2 by 2. This works for any dimension, but we're not going to do anything beyond 2 because we don't have linear algebra as a prerequisite for this class, so I can't enforce you knowing how to take a 3 by 3 determinant, but I can teach you very quickly how to take a 2 by 2 determinant. So suppose each function f1 and f2 possess at least uh, n minus one derivatives. Really just one derivative in this case. The determinant of f1 and f2 and its derivatives can be expressed as, so you say the Wronskian, so W, of f1 and f2 is equal to the determinant, so it's a matrix operation, and this is just a formula. So the formula of this determinant is going to be AD minus BC, which translates to F1 times F prime 2 minus F2 times F prime 1. You can write it whatever order you want in terms of the multiplication, but it's the same thing. You're just multiplying. Um, and this is called the Wronskian. Wronskian. So what can we do with this? Well, we can test for independence. And so here's the theorem. Let y1 and y2 be solutions to a second order differential equation on an interval I. And I want to make sure, because depending on the textbook, they might state it in this theorem. I will probably just say it, the fundamental set of solutions. Yeah. Fundamental set of solution is linearly independent if, when you take the Wronskian of y1 and y2, does not equal 0. Now, what happens when it does equal 0? It's just inconclusive. So if Wronskian equals 0, inconclusive. It can still be independent, it's just the Wronskian doesn't tell you. Okay, just note that. A fundamental set of solutions are solutions to a differential equation that are linearly independent. I won't abbreviate in this class. That's all. So if you see fundamental set of solutions, they're just saying they're independent. That's it. And all we really need to do is just plug in our functions, take some derivatives, and find the Wronskian. That's it. That's all you gotta do. So let's do an example. Is the set e to the negative x, x e to the negative x, linearly independent? So, first step, as always, is formula. So the Wronskian of y1, y2 is equal to y1, y2. The derivatives are in the second row. If you wanted to do more than two functions, you would just make this bigger, like so y1, y2, y3, and then you would have y prime 1, y prime 2, y prime 3, and then a second derivative, so y double prime. So you have to have square matrices to be able to do what's it called? Determinants. And however much you write for the formula, completely up to you. The one thing I do tell students, because this is a very common mistake, is, and I'm going to emphasize this with the Sharpie, this is a minus sign, not a plus sign. Now, if your coefficients have negatives, it can become positive, but I've seen people do mental math and get the sign wrong. So you got to be careful, right? Very careful with the mental math there. Step 2, label y1 and y2. Doesn't matter which one you call which. You'll get the same answer. It's independent of order. Step 3, derivatives. So y1 prime is going to be equal to negative e to the negative x, chain rule. And then the derivative of y2, this is a product rule, right? F prime g plus fg prime, your product rule. So f prime g plus f times g prime, like that. And then step 4 is to plug in. So e to the negative x. Make sure you give yourself enough space. I always short myself space on these, and it's kind of annoying to write later. And then this is going to be negative e to the negative x. And then this is e to the negative x plus, oops, I guess minus, right? And then plug in and evaluate. Went to one step. And so what I end up getting is e to the negative x times e to the negative x minus x e to the negative x minus x e to the negative x times, I need a little bit more space, and I get negative e to the negative x. And then I just got to simplify. So we're going to have to combine like terms as we've done before. So remember, x to the m, x to the n equals x to the m plus n. You just add them together. So we get e to the negative 2x minus x e to the negative 2x plus, because you get a minus minus right here, x e to the negative 2x. Cancel, cancel. I get e to the negative 2x, which does not equal 0. So the answer is yes. It is linearly independent. And that's it. That's all it comes down to with the Wronskian. It did not equal 0, so therefore they are linearly independent. All you have to be able to do with the Wronskian. Now, what they can do to make it challenging is just make the derivative more challenging. Um, and so you'll just have to be able to make those manipulations and make sure that you practice the basic derivative rules like product rule. I don't think they'll throw a quotient rule at you. It would just be too much work in that context, right? So definitely don't want to deal with that. So they are linearly independent. They are a fundamental set of solutions. So follow-up question that they could ask is y1 and y2 a fundamental set of solutions? The answer is yes, because they are linearly independent. That's why. So you would just put yes, they are a fundamental solution. Another question that they could ask you is like they could give you an initial condition and be like, what's the largest interval where the solution exists, or they could give you a coordinate or, stuff like that. So they can change up the problem a little bit. But all in all, that's kind of the same idea. So I can give you a coordinate and just ask you, stuff like that. So other than that, that's the Wronskian, right? That's basically what they're going to ask you is to do something like that. So where I'll end this section is kind of just a what do we gain out of this entire discussion of what we just did? Like, what value do we get out of it? It's this really for this chapter specifically. So, um, for chapter 3, we get that for a second order linear differential equation with constant coefficients, the solution is as follows. AY double prime plus BY prime plus CY equals 0. Y is going to be equal to C1 Y1 plus C2 Y2. That's it. Sorry. That's what we gain. That's the solution. Now, what is Y1 and Y2? It depends. But that's what we gain out of this chapter, is like we basically prove that this is true for what we're going to be doing for the rest of this chapter. Okay? And this is what we call the homogeneous case. Now, just as a preview to the non-homogeneous case, if g of x does not equal 0, then y, sorry, not y, a y double prime plus b y prime plus c y equal to g of x, we'll have the solution y equal to C1y1 plus C2y2 plus, and I'll use a different letter, let's call it A, yp for what we call the particular solution, or the, yeah, it's called particular solution. And so this right here is going to be the homogeneous, oops, and this is going to be the non-homogeneous. Can't spell homogeneous right now, even though I practiced for a long time. Nope, can't spell homogeneous at this exact moment. That's kind of funny. There we go. That's going to be the solution for non-homogeneous, 3.5 and 3.8. Notice that they both have C1, Y1, C2, Y2. It's just the non-homogeneous has this extra part. And solving for that extra part is just as time consuming, if not more time consuming than the homogeneous part. And that's where it becomes quite interesting, but not as fun in terms of using partial fraction decompositions or stuff like that.